Good afternoon, everyone. Welcome back from lunch. My name is Sharif Ghazzawi. I'm an engineer at Resonate.
And my name is Benoit. I'm excited to present at this year's SpringOne conference. In our half hour today, I'm going to walk you through one of the challenges that all big data companies face, the fast, dynamic querying of massive amounts of data with sub-second latency. First, let me tell you a little bit about Resonate and give you some context into why we do what we do. For those of you that don't know, Resonate exists to help brands and advertising agencies identify their best customers, to understand their likes, dislikes, motivations, and values so they can find more of them out in the world. Brands like Disney, Intuit, and E-Trade use our data and our platform to discover meaningful insights about their customers and prospects to develop creative messaging and drive their advertising campaigns. We're located nearby in Reston, Virginia, and we are hiring. We have about 10,000 different attributes that we can give all of our customers about the people who go to their websites, view their ads, or buy their things. These range from basic demographics to political affiliations, buying behaviors, motivations, values, all kinds of things. Our users can build audiences combining these things. For example, moms with kids who are saving for college. E-Trade can then know what those people's motivations and values are, find the shows they watch, and how to message them on value savings, safety, whatever. We model 10 million cookies every day for a total of 200 million cookies modeled online, ready to query at any moment across those thousands of different attributes. We then track those across thousands of different sites. So in terms of our large numbers, we have 1.7 trillion total predictions online, 22 billion total site hits online, ready to be queried and analyzed within seconds. What do we do with this data? So for example, we might want to tell our users how many cookies hit their homepage yesterday that we've modeled as female Democrats. How does that compare to the general population? What this breaks down into is a bunch of set operations. So we have the set of cookies that we've modeled as women. We have the set that we've modeled as Democrats. And we have the set who have hit our client's homepage in the past day. We need to get the count of the intersection of those things, and then we're computing a ratio. So we're dividing that by the number of users that we've modeled as female Democrats, and that gives us an insight. So we could say something like, female Democrats are 158% as likely to visit your homepage as the general population and constitute 17% of the users of your site. And then our clients can use that to change their marketing messages or know who they're reaching. Are they reaching the people that they want to? Those sorts of things. Our reports have thousands of different attributes. So that was just one. We need to compute thousands of different data points like that. This is a scatter plot showing all of them at once. You also have other views showing the actual numbers. What's important for this is each insight report requires thousands of these set operations to be performed within seconds. So how do we do that? The key takeaways that I want to give you here. First off, Geode can be used as more than just a simple key value cache. It can run it can run functions on data in memory. This is extremely powerful. It's something that wasn't really discussed much yesterday at the Geode Summit. I'm also going to talk about probabilistic data structures, what they are, and how they can be used in many industries to estimate counts to perform set operations at scale. And then we'll also talk about our experience building a Spring Geode architecture that was both performant and scalable. First, quickly, what didn't work? Our initial solution was built using HBase. I don't want to knock HBase. We were using it completely inappropriately. We had bitmaps consisting of all of these 10,000 different attributes. And we were doing sequential scans, getting the exact count of the number of female Democrats or whatever it would be. We had a 40-node cluster, a bunch of big, beefy machines sitting in our data center. These queries were taking upwards of 30 seconds to run, and if we had more than two users at a time, it could bring down our site. We were essentially using HBase as an in-memory database, so showing where we might go with the direction there. And then we made an interesting discovery. There's this whole class of things called probabilistic data structures. We had essentially a counting problem, and you probably do too. Most of our problems, most of the problems in big data are counting the number of likes or the number of hits, the number of unique IP addresses, all those kinds of things. Our users don't require exact precision. We're not a bank. If your bank told you you have approximately $10,000 in your account, well, that's not good. But if we said you had approximately 10,000 female Democrats hit your site yesterday, that's close enough, right? We don't need to know that there's exactly 10,382. These probabilistic data structures can estimate the cardinality of a set, that is the number of unique items in a set, the number of unique IPs that hit your website yesterday or anything like that. What's most important, what's most exciting is this can be done in a fixed amount of time and space. So you can decide how large is your data structure going to be. That affects both the precision as well as how long it will take to run those operations. But most importantly, it's fixed, it's consistent, it's going to be a order of a big O of 1 operation there. Now there's a bunch of different probabilistic data structures out there. Hyperlog is one that we've used. We also use Bloom filters elsewhere. The one that we ended up using for this project is the Yahoo Theta Sketch, developed by the folks over at Yahoo. So this gives you an estimated count in a fixed time and space, but most importantly for us, it supports set operations. So what that means is that we can perform all of those intersections, unions, all of those kinds of things that we need for this. I pulled a code sample from their site. I invite you to go to that website listed there at the bottom if you want to learn more. But you can see here we're building two different sketches. Each contains 100,000 unique keys with some overlap between them. And then down there near the bottom, it computes the intersection of those two sketches and gets you that count. So very simple, very straightforward to use. The output of that intersection is itself a sketch, so I can chain that and do more operations with it, compute another intersection with that, just like I did in my example a few slides ago. Now, the problem for us was these sketches began multiplying like rabbits. Sketches can't contain any additional metadata, so it just has the existence of an item in a set, but no more information about that thing. And we found for our particular use case, we needed to store a sketch for each attribute, for each tag. We also had to have different sketches for different ranges of time, so that we could support time-based queries as well. We ended up with an O of n squared problem there, that's not great, but it's kind of where we ended up. Next thing we knew, we had 150 million sketches. Each one was only 16K, but they stretched across 2 terabytes in all. So we needed a place to store all of those sketches. We wanted something that was fast. We wanted a distributed in-memory store. We wanted off-heap memory so that we could avoid garbage collection, so that we wouldn't have pauses when our users queried this. We wanted the ability to run calculations close to the data, that is, run those sketch operations right where the data is. And then we wanted things like read-throughs, eviction, fault tolerance, all of those scalability things. We needed a distributed in-memory database. We considered a few. We had used Redis elsewhere in our system. We use it as a side cache on our application. We were concerned about some of the scalability of that, as well as the fact that it couldn't run Java functions, as it supports Lua script, but not Java. We also considered Hazelcast, which was a strong competitor there, actually met most of the needs of our use case. But it didn't support the off-heap memory. So at least not in the free edition, and being a startup, we can never spend money on anything. So we ended up with Geode. Geode fit the bill. We're also just big fans of the Spring frameworks, and knowing that it was supported by our friends over here helped us out. And now Sharif will talk about the overall architecture of our system.
Thank you, Evan. So Evan spent a few minutes talking about the problems Resonate had, why we decided to use Theta Sketches. And I'm going to talk a little bit about the system we built out to meet those requirements. So on the screen here, you'll see a 10,000-foot view of our system architecture. At the bottom there, you'll see Amazon S3. Those 150 million sketches that Evan talked about earlier, those all live there. So when a request comes in through our UI, our backend Spring Boot infrastructure receives the request. It then calls a function on Geode to perform those set operations that Evan talked about earlier. In order to do this, it needs the sketches in memory. So it receives a request. It says, hey, I need to intersect these 3 or 4 sketches. If the sketch does not already exist in memory, it is read through from Amazon S3. For this, we developed a cache loader that will load data from S3 if it does not exist in memory. So the 2 things we did to modify Apache Geode was the set operation functions and the read-through function from S3. How does data get into S3? As Evan mentioned, we track online behavior, and that changes day to day, which means our sketches need to be updated on at least a daily basis. So we still use Hadoop to build out these sketches. So when we have an updated sketch, Hadoop builds it out, and that lands in Amazon S3. Amazon S3 will then fire a object updated event that is ingested by a Lambda function, and that Lambda function in turn produces another event on RabbitMQ, which is a sketch updated event. Our Spring Boot app picks that event up and then evicts that sketch from the cache. So the next time the application needs to use that sketch, it will be read through again from Amazon S3. You'll notice I've got little Docker icons there that just signifies what things we have running in Docker. So one thing I'd like to point out about this slide is there's nothing unique here to the marketing or advertising industry. We're using sketches to represent online user behavior. You could use sketches to represent the set of IPs that are flowing across the routers in your infrastructure to get greater insight into network traffic. You could use sketches to represent the customers that, if you're a credit card company, the purchase data behind your customers to gain insight into customer behavior, maybe even identify fraud and malicious behavior. So this is our system architecture. So let's spend a little bit of time talking about how the system behaves and what this buys us. So right out of the box, we have data locality. Our sketches live in memory, and our functions execute directly on those sketches. No need to shuffle sketches around between nodes. In terms of performance, this was a great boost. What was before an O of n sequential scan now becomes an O of 1 lookup. Also, as Evan mentioned earlier, sketches can now be chained in operations. So in the example Evan gave earlier with the women Democrats and women Democrats that hit your homepage, with HBase, we were counting women Democrats twice. With this, we could produce a sketch out of women Democrats, get the count there, and then instead of having to reproduce that sketch, use that sketch to intersect it with the number of users that hit your web page. Fault tolerance and resiliency. Currently, our system could tolerate the simultaneous failure of up to 4 nodes. That's our best case scenario, and that all depends on Geode's quorum calculations. It could actually survive the failure of more nodes if you give the quorum time to rebuild. We heavily leverage AWS Elastic Load Balancer, and what that does is if a Geode node is unhealthy or misbehaving, it will kill the Docker container, bring up a new Docker container with the server, and it's business as usual. And of course, we distribute all our nodes across AWS availability zones, so if the AWS Northern Virginia region is having a bad day one day, we're not out of business. And then as far as scalability, we just add more servers, rebalance, and move on. This is head and shoulders over what we had going with HBase. So for the next couple slides, I'm going to talk about various aspects of Geode and our experience in trying to build this out. The first thing I'm going to talk about is Geode regions. Geode gives you a lot of flexibility with what type of regions you have. They could be persistent, partitioned, replicated. And right out of the gate, we're a bit naive, and we said we want all the things. We want persistence, we want partitioning, and we want replication. However, this really didn't meet our needs. So with a persistent node, if a node goes down and comes back up, before that node is made available, it will check to make sure that it has not lost any of its persistent data. That takes time. And if the whole point of swapping out a node is to keep operating, this was just too slow. In this case, we see Geode kind of favoring consistency over availability. Replication. So when a new node comes up and joins the cluster, before it's made available, it will make sure that it is honoring the replication configuration. You know, it has all the data from other nodes that need to be replicated, and its data is replicated elsewhere. This also took time. So both of these things made it very hard for us to swap out nodes quickly and kill dead nodes. So at the end of the day, we went with just partitioned regions. Partitions allow us to scale out horizontally, but as far as data persistence and durability, we made that a concern of S3 only, and Geode didn't have to worry about it, and that works great for us. As I mentioned earlier, we run Geode servers and locators in Docker containers, and we had a bit of a challenge here. So the recommended way of standing up a Geode standalone node is through using the gfish utility. And what gfish will do is it will spawn a locator or a server in the background, and then it itself will die. Unfortunately, Docker requires a foreground process to be running in order for the Docker container to stay up. So what we had to do here is we actually had just a dummy process that starts up next to a Geode that runs in the foreground that keeps the Docker container up and alive. Geode and ECS. So we deploy our Docker containers on ECS, and Geode locators store state while they're operating on disk, and it's hard-coded that state has to be kept on local disk. This is a problem with ECS because you're not guaranteed out of the box that your Docker container will always come up on the same node every time. What we'd really like to see is maybe a kind of a way to plug in your own storage mechanism there. But for the time being, what we did is we tightly coupled an individual locator to an individual ECS instance to make sure it comes up on the same instance every time and has access to that state when it comes back up. Our original prototype we tried to use Apache Geode using Spring Boot Data Geode. And in that architecture, what we were doing is we were launching Geode embedded within a Spring Boot app. At the time, this did not work for us because at the time, there were no lifecycle hooks into the Geode process that Spring had access to. So if the Geode process was unhealthy or misbehaving, the Spring Boot app side of the app really didn't know about it. I'm glad to hear that since then that there are lifecycle hooks in Spring Boot Data Geode, and it might be time to revisit that decision. But for now, we're running it as a standalone process launched by gfish. How we manage configurations for Geode. So Geode comes with a very tightly integrated configuration management system. So what you do is you produce a configuration, you upload it to the locator, and the locator is responsible for distributing that configuration to all the servers. A lot of organizations, including us, already have some type of a configuration management infrastructure, whether we're talking console, Zookeeper, Spring Cloud Config. So it would be nice to see us be able to kind of swap out these configuration management solutions instead of having to do things one way with Geode and then another way for all of our other systems. So that kind of covered kind of the various aspects and challenges and lessons learned around Geode. But one thing I want to stress is as early, when you're working with Geode, you're building a distributed system, and with any distributed system, make sure you understand the consistency, availability, and partition tolerances guarantees that the technology provides, and how that translates into your system. I'd also recommend resiliency testing as early as possible. Don't save it till right before deployment. Once you have a prototype, start testing immediately all the ways your system can fail, how it responds to it, and kind of use that to further drive decisions, design decisions.
Great. So in in summary, we deployed a Spring and Geode architecture containing Yahoo Theta Sketches. It significantly improved our platform performance, dropped our reports from about 30 seconds down to less than 5 seconds. It reduced our operating costs by over 90% from our HBase implementation, reduced the number of servers needed from 4 down to 5. It increased our scalability. We can now scale horizontally to add more users and more data, and most importantly, support concurrent users now. It greatly simplified our operations with the event-driven architecture to replace sketches. Let's just patch things, update things in near real time. And it increases our resiliency with a shared nothing, self-healing, containerized cloud architecture. So just a reminder, Resonate is hiring in Reston. We have a bunch of different openings. So for Spring engineers, big data engineers, including Spark, Geode, Hadoop, and Kafka, DevOps engineers, AWS experience, and then also Ember.js user experience engineers. If you were interested in this talk, then we are very interested in talking to you. And I will open up the floor for any questions. Sir in the front.
You talked about sketches being in S3 and you guys loaded afterwards, right?
Mm-hmm.
Mm-hmm. What I was asking is, what's the load size? Like, what's the size of these sketches, and how do you basically pass the data through and create intersections? Do you use OQL, or you just like do some kind of a Java API to pass through those?
Sure. So
how do you do the crunching?
Right. So your question is, how do we actually run the queries in Geode on the sketches, and how large are they?
Yeah, so our sketches are in the single-digit megabyte size, but you can control that. So I think Evan talked about the value of K earlier. With a higher K, what that means is your sketches on average will be bigger, but you'll have greater accuracy. With a lower K, you have smaller sketches, but you sacrifice on accuracy. And as far as how we perform the intersections and the set operations, we don't use OOQL or anything. We have a Geode function that we wrote that literally runs very similar code to that Yahoo sketch code that you saw there.
Yeah, so it'll just do a get operation and then do its thing on the sketch, yeah, and then return that, yeah. So we use Antler to parse the expression, so it passes a Boolean expression of the ands and ors and all that, and then it uses Antler to break that down into the component sketch functions, runs those things to build it up and return the actual count. One other thing I'd like to mention, actually, when we do the read-through from S3, one thing that we found early on was we were doing read-throughs of individual sketches. So every time an individual sketch was needed, it would go out to S3, load up that sketch. That ended up being really slow. So what we did was we actually bunched these sketches together in what we called parcels of about 1,000 sketches each, something like that. Mm-hmm. Because we knew that if you want one sketch for a tag, you're probably going to need all of them for a tag. So we might as well just load them 1,000 at a time, and that batch read was a lot faster than individual read-throughs for each sketch. Other questions?
So,
oh, sir.
No, you're good. No.
I also saw in your architecture diagram you had like data being moved from S3 to Geode, right? Mm-hmm. But you had alternate way also, where it was going through lambda expressions to rabbit.
Yes, so what I guess wasn't clear in that slide was that alternate route was not sketches. That was not sketch data that was being moved around. Those were just events signaling that a new sketch had landed in S3 so that we could evict the old one from Geode, and on the next read, we would read through from S3.
That's kind of my question.
Yeah.
Why would you not take the lambda approach rather than using cache loaders into Geode?
I don't think we consider that. So you mean actually taking passing the sketch along through the messaging pipeline to Spring Boot and then loading it into Geode? I'm not sure if we considered that, but that's interesting. I'll have to give that some thought.
Yeah. Sure.
Follow on. So you're both loading 1,000, but could you use caching in Geode itself to just have a cache?
So we wanted to only load those sketches into Geode that we were actually going to use. So we had the concept of some of the data would be hot, some of the data would be cold. Of the thousands of tags and sites and things that we have, only a fraction of those get used on a given day. So the idea was to only load those ones that will be hot up into the cache where they'll reside until they're evicted. Does that answer your question?
Yeah, it sounds like you can tell pretty well what tags set to load.
Yeah, exactly.
Yeah.
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 So we load the entire set, and then that stays hot for the user's session. And we considered a lot of other cache warming ideas, like when a user logs in, maybe we'll load up all of their tags, sketches, or maybe like the top 10 that they've used, or 100. There's a lot of different ways to optimize that. The key thing was what data is going to be hot, what data is warm, what data is cold, and that was something that again, if you guys are trying to do this sort of thing, think about it in those terms. You don't have to have everything pinned in memory. You can keep the size down. A lot of what we did early on was just the sizing of things. How many sketches, how large are those sketches? We had big Excel spreadsheets showing, okay, assuming this number of users, this number of sketches, what's the number that we need to hit? Yeah, great, thank you. Other questions, sir?
So it sounds like you lazy load the data grid. How big does that data grid generally get on a given day? And do you auto scale? Are you using Docker to auto scale during the day, or is that just from an operational standpoint?
Mostly from an operational standpoint.
Yeah. We run right now a 5-node server cluster, and we've scaled it up just for testing, but the 5 nodes have been more than sufficient to meet user demand up until now.
How big is that data grid across 5 nodes?
Yeah, it's partitioned, and I think last time I checked, we had on the order of 20 million keys in memory. So about 20 million sketches, but that could change depending on daily load.
Great. Other questions? We have about 3 or 4 minutes left. Sir?
A couple of questions. I know you guys mentioned you reduced operating costs by 95%. What contributed to that? And the second piece around Redis, right? That was one of the things you considered. What is the benefit? I know you kind of covered it at a high level. What's the big difference you got out of Geode compared to Redis?
Sure. So the first question is how do we save costs, and then the other one is why didn't we not use Redis? So the main cost savings was the reduction of the number of servers. So we had 40 HBase servers, and we're down to 5 Geode servers supporting actually more users than we were with that. So just a reduced cost there, as well as just the administrative overhead of that many servers. And then Redis, we're definitely big fans of Redis elsewhere. We use it as a side cache. Our concern with it for this largely was that it couldn't run those sketch operations. The Theta sketch library was Java code, and I don't believe Redis can support running Java functions in memory on that data. We wanted to make sure, again, that the data was kept local to those functions. Obviously we could have had sketches in Redis and then loaded those into Spring and then had Spring run the sketch operations. But the key thing here was having that in-memory database not just store the data, but also hold that data, also run all those sketch operations on the data, so that we didn't have to swap data all over the place.
And as far as those 40 nodes, those were running at capacity before. Now with the 5 nodes we have, we still have room to grow before having to add another server.
Yeah, we need more users. Yeah. Other questions? We have a few minutes left. Actually, maybe one more question. We have time? Anybody else? Well, great. Thank you so much for your time. I hope you enjoyed the rest of the SpringOne talk here. You can rate us on the app, I think. You can give us some feedback. Hopefully this was a good use of your time. And again, if you are interested in more about Resonate or about Sketches or Geode or anything else, we'd love to talk to you. Thank you.
Thank you.